Okay, so the next topic is going to be talking about how I can frame these problems to you. So one thing you're going to come into contact with is that it's going to be very easy to kind of recognize problems and solve them from a certain perspective, but it's going to be it's surprisingly difficult whenever that perspective is slightly changed. So what do I mean by that? So an analogy of that is going to be if you consider writing with your left or your right hand. So whenever you're writing, you either found out at an early age that you were a lefty or you were a righty. And so you then, train your hands to be able to write with that particular hand. So me personally, I'm right-handed, and so if I was to write my name, this is the way that I would write my name. So overall, I don't have the best handwriting in the world, but it's relatively legible, I'd say. So that's me writing with my right hand. So now the other way to do this is if I wanted to write my name. This is probably going to look very bad, but now, like, comparing and contrasting, you can't see me, but this is me trying to write my name with my left hand. So if I was to try to write my name with my left hand, obviously this isn't working out so well. It looks, it's still legible, but overall, it's much less pretty, I guess. So left hand is on, down below, and right hand is, on the right. So left hand versus right hand. So left hand, and actually that's pretty bad, but right hand on the right. So obviously I'm better at writing my name with my right hand versus my left hand. And the lesson here is that I'm really good at writing my name with my right hand because I've trained that right hand to write relatively legibly. I haven't done any training with the left hand to try to write in a legible fashion. And that's all well and good because my right hand's never going to be chopped off, hopefully. But in organic chemistry, the analogy is that you have to be ambidextrous. You have to be ambidextrous. You have to be able to solve problems from multiple angles and using multiple perspectives. So what the lesson here is that you need to train your brain to solve problems using both your left hand and your right hand, which means trying to solve problems. If I gave you, let's say, a problem like above, where I gave you the starting materials and the reagents, you should be able to predict the products. But I could also frame the question from a different perspective, and this would be kind of using your left hand or a different way of thinking about the problem, which is I've given you the products now, and it's obvious that, well, we have the same kind of molecule where we have an alkane with a bromine, so we know that in order to get here, we have to add HBr and some alkene. But it's going to be very different whenever you actually try to, dig in and try to predict the starting materials. So, so this is one way I could phrase a question to you is that, obviously, if you see this type of material, you need to add hydrogen halide. In that case, it's obvious HBr is going to be what's needed. And then one thing you're going to have to be able to recognize is that, well, okay, I have an alkane, and that means I need an alkene. So your goal is then going to be, well, where the heck is that double bond going to be? Is it going to be right here, 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 over here? And that's part of the challenge. So let's go ahead and I'm going to number this problem or this molecule. So let's give these guys numbers just so we can talk about it. So 1, 2, and 3, and 4. So go ahead and pause the video and try to predict where that alkene or that double bond is going to be, because we know it's going to be somewhere, and we know it's going to be immediately adjacent to the carbon that holds that bromine. We know that it's not going to be something like over here or anything like that. So let's go ahead and pause the video and try to predict. Okay, so after you've paused the video, hopefully, and you try to predict the product, you're probably in one of two different camps. So I'm going to try to draw this 6-membered ring, and I'm going to go through 2 possible products that you could have predicted. And if you got one of these products, it's not going to be the correct product. Don't worry about it. It's just one of those things that you have to mess up on at least once or twice before you get the right answer. So If this is carbon 1 and 2 and 3 and 4, I'm going to copy paste. And this is our general like template, I guess, for what we could potentially have. And so we could either do one of two things, and these are the major types of answers that you see, is that people try to put that double bond between either carbon 1 and 2 or between carbon 2 and 4. Now, really, there's a third option, and that could be putting that double bond in between carbon 2 and 3, but really, there's no real difference between the, let me just go ahead and put letters here, A, B, or C. There's no difference between B and C because, again, this carbon 1 to 2, this carbon 1 to carbon 2 can rotate in free space. So really, that 3 can end up being where the 2 to 4 bond is, and that 4 can be where the 2 to 3 bond is. So really, this guy is kind of a repeat over here. So we're just going to kind of ignore him for now and not worry about him. So these are the two potential products, either or starting materials, having the double bond either between 1 and 2 or 2 and 4. And if you chose this molecule on the right as being your product, you are absolutely correct. So it's going to be this molecule right here as your starting material. That's going to be the better starting material. And we can either rationalize this through a mechanism, or we can rationalize it using the rule that we just learned in the previous video, Markovnikov's rule. And that rule told us that our electrophile is going to add to the carbon with the most number of hydrogens. That's going to give us the major product. And again, for this HBr reaction, the electrophile is our H+, or our H. So in this case, if we think about that H adding to the carbon with the most number of hydrogens, let's think about how many hydrogens are on 1 versus how many hydrogens are on 2. And this answer should be instantaneous to you by now, which is carbon 1 and carbon 2, they both have 0 hydrogens. So there's really no preference one way or the other. Okay, if you think about starting material B has 2 hydrogens on carbon 4 and 0 hydrogens on carbon 2. So in that case, it's going to be, even though that hydrogen could go on 4 or on 2, according to Mark, the major product is going to have those hydrogens go on 4. So in this case, B is going to be our product or starting material that can give us this as our major product. Now, A would give us this as a product, but it's going to be very inefficient because it's going to really, A is going to give us 2 products with equal proportions. It's going to give us this molecule on the left, and it's also going to have another molecule with the bromine on carbon 3. So if we use A, we're actually going to get 2 different products, and it's going to be a combination of the bromine being on carbon 2 and the bromine being on carbon 1. So A is going to give us both of these in about a 50-50 mix. And so let me go ahead and color these guys in. So if this is the molecule that we use, so this is A, if we used A, we'd get about a 50-50 mix here, about a 50-50 mix, because there's no preference, according to Markovnikov, one way or the other. And so then if we use B, molecule B, B for blue, blue for B, if we use molecule B as our starting material, we'd actually get a totally different percentage. So we get this, and we would get this molecule on the right, where instead of adding to carbon 2, the bromine could add to carbon 4. So really in this case, there would be a preference, according to Markovnikov. So in this case, we might have a very different distribution. So I'm just going to make up a number. I'm not sure what it would be, but maybe like 80% this molecule and maybe 20% this molecule. So I guess the point here is that there are 2 potential ways to get the molecule that we were shooting for. The molecule that we were shooting for was that molecule with the bromine on carbon 2. And so if we think about efficiency of reaction, and we thought about, just how good we were at putting that bromine on carbon 2, if we utilized the starting material A, we would have gotten that bromine where we wanted it, 50% of the time. But if we had used molecule B, then we would have gotten the molecule where we had wanted it, a much higher percentage of the time. So, we're always striving towards being as efficient as possible and getting as much of the molecule that we want as possible. Because otherwise, it's kind of a pain in the butt to separate molecules. So this would be a much easier purification than this right here. So in terms of practicality, molecule B is a much better starting material.